Hi everyone, welcome to another video on gold, and this time I will translate science into exploration vectoring. The diagram I will show are from Williams-Jones et al. 2009, and instead of treating them as a pure geochemistry, I will walk through how they can sharpen our exploration strategy in the field. The goal is simple: turn solubility curve and speciation maps into practical vectors you can use when mapping, sampling, or planning your drill holes. So if you find this interesting, you can watch the other videos in the coming soon playlist where I want to expand on the entire paper, always with a focus on how it can refine the exploration targeting. So as I said, the idea is simple. If we understand which ligand carries gold and under which redox buffer the fluid sets, we can predict what processes will cause gold to drop out. That knowledge translates directly into field vectors. So think of this as a roadmap. First, use mineralogy and fluid inclusion to pin down a redox condition, ligand, and temperature, then overlay oxidation, boiling, or sulfidation zones on your map. Where these two overlap, you have got higher odds of gold deposition and better drill core targeting. Let's start with the left diagram, which is fundamental in understanding the ligands. So below 350 degrees C, hydrogen bisulfide carries gold. Above around 350 to 400 degrees C, chloride competes and dominates. So use fluid inclusion, thorium, and salinity to place your system on the spectrum. This is obvious. Also, you may decide which redox buffer apply to your area of interest. If you see hematite, magnetite, anhydrite as a stable alteration pair, use hematite magnetite buffer for FO2 as shown in panel A, and you may expect more oxidized sulfate stable conditions, and you can see the gold solubility rebound as you can see in the panel A. If you see pyrite, pyrrhotite, magnetite co-evolve in the ore stage, use a pyrrhotite magnetite buffer in panel B. In this buffer, total sulfur commonly drops on cooling, so gold solubility does not rebound. Precipitation can persist down temperature. In general, a modest 50 degrees C drop between 500 to 300 degrees C can dump over 95% of dissolved gold. And I will explain later why and how does this figure show this. What is important here is to target cooling pathways. It is alone a quite powerful tool. If total sulfur falls during cooling, as you can see in panel B, the usual low temperature solubility rebound is not there. Expect continuous gold precipitation down temperature, so you may do sampling along the gradient for decreasing total sulfur. This means that upflow rocks scavenge sulfur as pyrite. The remaining fluids become sulfur poor, so downstream rocks receive less sulfide and less gold. Now we'll move to the right diagram where we can map three traps. The first is oxidation fronts. So hydrogen bisulfide crashes and gold drops out where reduced sulfur-bearing fluids hit hematite hosts or oxidized water. So in the field, we need to walk the redox front and sample across it. To find the redox front, trace where magnetite turns into hematite, goethite, or anhydrite appear in the field, or where even pyrite rims are replaced. This is our redox front. Second is to map boiling horizons. Boiling stripes hydrogen sulfide into vapor and raises pH. post-cutting solubility. We should log boiling texture like bladed calcite quartz or comb quartz, etc., and confirm with existing vapor and liquid-rich inclusions. I will have a complete video on the boiling texture soon. Third is a sulfidation halos. Pyritization and iron-bearing wall rock consumes hydrogen bisulfide. So we need to map pyrite intensity and replacement and expect gold pinned to those halos. In summary, use mineralogy and fluid inclusion to infer redox condition, ligand and temperature, then overlay oxidation, boiling and sulfidation maps, and finally prioritize overlap zones. In the next set of videos, I will dive deeper into the geochemical aspects of these two diagrams in more details.